Hello, Math B Honors students. Welcome to Module 5, and today's lesson is 5.1a on exponential form. This is a really important lesson. We're going to give a little bit of a preview of what exponential forms are, and later on we're going to practice some order of operations. So please watch this video carefully and take notes along the way. Okay, it says at Manuel's new job, the company is offering him two different options for his retirement plan. Option A, 100,000 the first year, and then every year after that, he will get $100,000 more than the year before. Sounds pretty good. It sounds somewhat linear, right? He's growing at a constant rate every time. Option B is $10 the first year, and then every year after that, he will get 10 times as much as the year before. Okay, so you have to decide which one is the better choice. So let's just go ahead and write it. Year one, option A, he would get 100,000. And year one, option B, he would only get 10 to the 1 power, right? I'll go ahead and use another marker to show this. 10 to the 1 power. Now, that seems really low, but you can see that over time, it will start to really ramp up, right? Year two, you really only get one more extra 100,000. I'm going to go ahead and finish this. Year three would be 300,000, and so on. And gaining this every year is actually really, really good. It's still a lot of money, as you can see. And really, you don't even need that much to survive at that point. But that's a lot of money for annual retirement, income, I guess. But year two, let's look at year two for option B. Year two would be 10 times 10, which is really 10 squared. And it's only $100. So it still pales in comparison to year two, right? Would you rather get 200,000 annual income or just $100, right? Doesn't seem worth it to do option B, but as you can tell and as you can predict, as the years go on, it really, really increases its value, right? And as long as you're patient, you can see how exponential functions can really be much more valuable. Okay, year three is 10 to the third power, which is 10 times 10 times 10, which is 1,000. Year four is going to be 10 to the fourth power, which is 10,000. Still not even close to 400,000. But you can see in year five, I'm just going to write 10 to the fifth for short, and that's going to be 100,000. So we're finally in the same ballpark. Still 5 times smaller than year five in option A. But year six, if you were patient enough, and hopefully in retirement, the one thing you do have is patience. 10 to the sixth power would be finally that $1 million mark. And that's an annual income. So what option should he choose? Well, it really depends, right? Like if you want to have a very, very lavish retirement and the first few years of your retirement, you want to party like crazy and spend all this money, that might be worth it to go with this option A. But if you have time and you can invest your time and wait patiently for year five and year six and even year seven, you can see that the amount that you get, the amount that you are able to gain each year will be significantly higher in year six and beyond. Okay, so if you ask me, I would say I would choose option B, because the annual income from year 6 and beyond is significantly higher than option A, right? This is kind of like the theme of this entire module, right? Linear growth versus exponential growth. This entire time in Math Be Honors, we've been studying linear relationships, and now we finally get to see how exponential functions, exponential relationships can be much more powerful and can grow at a much higher rate. Okay. So let's go to letter B. It says, write an equation that could be used to find the amount of retirement Manuel would receive for any given year for option A and for option B. They kind of want you to write the equation, and we know how to write that, right? If you look at option A, you can see that he's gaining about $100,000 per year. So we know that that's linear, and we can go ahead and write that as y is equal to 100,000x, where obviously x is the number of years, right, since his retirement, right? Years of retirement, right? Not bad. $100,000 seems like a lot of money. I don't know if I could resist that. That's a lot. Option B, this is where we get introduced to the exponential function. Option B is, so you have your base of 10, and you realize that every year you multiply your previous year by another 10. And you can see how the variable is on in the a little bit higher than normal. It's not on the level of the 10. And this is what we call the exponent, right? This is literally the exponent. And x is the exponent here because it tells you how many times to multiply the base by, right? And the definition of x is still the same. Y, I'm going to go ahead and define y is money received. And I just spelled that wrong. Received. I before E except after C. Received. Money received in retirement. Okay. Okay, so now let's go ahead and go to the next page. And I think I'm going to use a different page because this is double-sided. So it says, use your equation for option B to complete the table of values. Okay, so I'm going to go ahead and write the equation one more time. It's y to the 10 to the x. So if you plug in 1, you would get 10 to the 1, right? And you get 10. 10 squared would be then 100. 10 cubed would be 1,000. And 10 to the 4th would be 10,000. Okay, now let's have a sketch, right? So years would be your x, and then dollar amount received would be your y. The first year is terrible. You only get paid $10, which is really, really insignificant. What's interesting is, we'll talk about it later, but when you plug in 0 to the exponent, 10 to the 0 power is equal to 1. Believe me, we're going to talk about this later, but I went ahead and just plotted that 1. In the first year, I also gained about $10, so it's barely any gain. The second year, I make $100, so that's about half of 200, right? The third year, I make 1,000, so then I'm right here, which is, wow, that's a huge jump. It's 10 times more than the original. And then the fourth is way, way off screen, right? It's not even on the curve anymore. And you could see it's like a roller coaster going up a very, very, very steep hill. And that's only the first 4 years class. So if you have the patience to wait, you can see how an exponential function, especially with the base of 10, is really, the rate of change is really significant. Okay. The equation y equals 10 to the x is an example of an exponential function or an exponential equation. Exponential equations are often used to solve problems involving biology, archaeology, and finance. An exponential equation is an equation of the form of y equals a times b to the x power, where a is the starting number or initial value, and b is the growth or decay factor, and x is the number of periods. Okay, exponential equations represent situations of extreme growth. Unfortunately, hate to bring this up, but you can tell from the situation that we're in, um, the coronavirus was growing at an exponential rate. It was not growing at a linear rate, right? So that's the clear and easy, realistic example of how something grows. Infections in life and in species grow at an exponential rate because the more people that are infected, the more easily infected new people will be. Okay. Um, okay. So I hope that made sense. Let's now start talking about the order of operations in which you uh, calculate and simplify something in exponential form. Okay, this is really important. Okay, please make sure your order of operations, the foundation is solid. So I'm going to go ahead and write PEMDAS, right? The order of operations. We know that this is parentheses, exponents, right? I'll write that down. Parentheses, exponents, multiplication, division, addition, and subtraction, right? And we know that we're always supposed to go from the top down. This so far this year, we haven't really done that many exponents. This might be the first lesson. So you can see that exponents is really, it has pretty much the highest priority in terms of things to do first. So if you see something like, obviously 2 is 4 cubed, well, if I were to expand that, that would literally be 4 times 4 times 4, which we know is 16 times 4, which is 64. Okay. Here, for number 3, you can see that that's negative 5 to the 4th power. Notice how the parentheses are protecting the entire base, including its negative. So if you wanted me to expand this, it would be that. Uh, Notice how this is an even function because there is an even amount of terms in this case, and we know that if there's an even amount of negatives, then my final answer will ultimately be positive, right? This is really just 25 times 25, which we know is 625. Okay, now let's take a very clear look at number 4. First of all, how does number 4 differ from number 3? Well, you could see that number 4, the exponent is attached to the 5, but it's not attached to the negative as it was in number 3, because number 3 had a parentheses around the negative 5, like the 5 and the negative as one. However, in number 4, you don't see the parentheses there. So technically, class, this is very important. Technically, number 4 is negative 1 times 5 times 5 times 5 times 5. It is imperative that you are able to tell the difference between number 3 and number 4. Okay, because the negative is not protected by parentheses, you kind of just leave it on the side, calculate 5 to the 4th power first, and then attach the negative afterwards. Okay, a lot of students cannot distinguish between the two, and they end up saying it's 625 here and it's 625 there, when in fact number 4 is actually negative 625. Okay, last one we'll do is number 6. You can see you got to take your time here. This is a minus, this is subtraction, but I really don't even care about it yet until I finally calculate what that is, and I calculate what that is itself too, right? Then I subtract the 2. Okay, so this is negative 7 to the 5th power. That's a big number. I don't even know what it is right now because it's a pretty large number. But it's really just negative 7 times negative 7, right? 5 times. We know that the negative is in the parentheses. So it's actually going to be a negative product, right? The answer will be negative. And it's really just 49 times 49 times 7, which is a huge number. So I'm going to use my calculator and I get 16807, but it's negative. And don't ever try to make this negative jump and distribute into that parentheses, right? This is an exponent, so you can't distribute the negative like we did in modules past. You have to respect the exponent here because in the order of operations, that's what you have to do first. So you have to do negative 9 squared, which not that bad. We know that that's literally just 81. And then you get negative 16807 minus 81, right? So negative 16807 minus 81 is literally just adding on to the negative, and your final answer is negative 16888. What do you think number 7 is? Go ahead and write in the chat on, or write somewhere what you think number 7 is. And let's take a pause break on this video and go to part 2 after this.